Analyzing constant velocity gave us the what. Now let's look at the why by analyzing balanced force diagrams. Newton's first law describes balanced forces. It's famously known as an object at rest tends to stay at rest. An object in motion tends to stay in motion until an outside unbalanced force acts on it. Objects that are at rest or stopped are a form of constant velocity. These represent balanced forces. Nothing is pushing more or pulling more. Objects that are at a constant velocity also represent balanced forces. These are objects that are in a constant state of motion and will stay in motion until an outside unbalanced force acts upon them. Newton's third law, most famously known as for every action there's an equal but opposite reaction. If you push on the ground pushes back. The earth pulls on you, you pull on the earth. All forces come in pairs. Newton's three laws are an observation of forces. A force is something that pushes or pulls. Brainstorm on your own anything that can cause a push or a pull on an object. To describe why certain motions act the way they do, we can look at the individual forces that cause the motion. We represent the magnitude and direction of these forces using force diagrams. A force diagram is a visual way of showing all of the forces acting on an object. This explains why an object moves the way that it does. By looking at the individual forces, their relative magnitudes and directions, we can decide if something is accelerating, is at a constant velocity, or if it's stopped. When we draw a force diagram, we always start by labeling the object with a dot. Each force is represented by an arrow. These arrows tell us a lot of information. The length represents the relative magnitude. The direction represents the direction in which the force is acting. So in this case, we have two longer forces that are balanced out. One is pushing up or pulling up. One is pushing down or pulling down. These two forces are also balanced. They have less magnitude, so the forces in the left and right direction are less powerful than the up and down direction. We have a force pulling or pushing to the left and a force pulling or pushing to the right. The forces always push or pull away from the object. Even if the object is being pushed, we want to see how the force is acting on the object. If I'm pushing to the right, the arrow is going to come out the other side and point to the right, away from the object. Once we've drawn the force diagram, we need to label it with all of the individual forces. The kinetic friction force is a force that acts opposite the motion of the object. So this is when an object drags along a surface or another object. If an object's friction prevents it from sliding or moving, we are looking at the force of static friction. This is a force that acts opposite of the likely motion. This is so much friction that an object cannot move. Imagine a box sliding down a hill. If it stops moving, it's because of the force of static friction. The force is pointed opposite of its path down the hill. It's pulling up the hill to prevent it from going down the hill. The force of gravity always points straight down. It represents Earth's pull on every object on the Earth. An applied force is a force that's applied in a direction described. So if I'm pushing a lawnmower forward, I have an applied force that's pushing forward. If I am walking forward or driving forward, I'm applying a force in a very specific direction, either by an engine or by me pushing against the ground. Tension forces are applied by strings or ropes. The normal force exists whenever an object is on a surface. The object pushes down on the surface pushes up. This force is applied by a surface perpendicular to the surface, so the force always makes a 90-degree angle with the angle of the surface itself. When we're dealing with balanced forces, we need to make sure for every up there is a down. The arrows need to be the exact same size. the magnitude needs to be the same. It's like an evenly matched tug of war. For every left, there is a right. For every left force, there has to be an equal magnitude right force. We know that we're dealing with balanced forces when we see a couple different scenarios. Constant velocity would be balanced. An object that stopped would be balanced. Speeding up and slowing down are unbalanced forces. This means that in these cases, one force is pushing or pulling more than the other. Let's practice drawing a force diagram together and labeling it. An object is pushed at a constant velocity to the right with a push against friction. Since we know this is constant velocity, we know that it's balanced forces. So I'm going to start by drawing the dot. That's our object. We need to ask ourselves which forces are present and are the forces balanced or unbalanced? Well, constant velocity means it's balanced. That means it's balanced in the right-left direction. Up, down, it's also going to be balanced. Unless it's accelerating upward or downward, it's going to be balanced forces up, down, left, and right. A great place to start with forces is always gravity. Gravity is always there and it always points straight down. So I'm going to label it F sub g. That's my gravitational force. For every up there is a down, for every down there is an up. So if I have gravity pulling down, then the normal force is pushing up. These are balanced forces, so the forces, the magnitudes of these arrows need to be the same. Now it says that there's an applied force to the right, so I'm going to draw my applied force. It's moving at a constant velocity, so that means that for every right there is a left. So I need to balance that out with the force of kinetic friction. If there was no friction, this would be an unbalanced force, and we would have acceleration. That box would increase and speed up to the right.